Following on from our previous video, we got to this stage here. Where we created this thing called time, and then time would drive the particle along our intended path. So we would imagine our vertical sheet of paper along our intended path. So this is our vertical sheet of paper looking like this, and it's a flat 2D sheet of paper, so we can actually draw it like this. And we created it in such a way that an increment of time would match up with an increment of the distance in our intended path, in our intended direction. So time matches up with s. We created it in such a way that time matches up with s. So we would now abandon time and just use s. So for given s, we would know the precise location of our particle in the x direction and the precise location of the particle in the y direction. So once we know the precise location, once we know the precise x and y location, we can bung it into the z function, and then that would then jump to the surface. So once we know the x and y location, we can work out the height of our surface. So this is our function diagram. So from that we can work out dz by ds, which was what we wanted to work out right from the start. The directional derivative, meaning the derivative in our intended direction. So this is what we're trying to work out. So remember from the chain rule, so now using the chain rule, you have to go back and familiarize yourself with the chain rule. So the chain rule, so looking at this, really you've got in effect you've got a machine here where you input s. I don't care what x and y, I don't care about the precise location of the particle. It will then spit out the height. So really I've got this diagram here where I insert an s and then I will get the height. But then I want to know dz by ds. So the question here is, looking at this, do I use partial derivative of z with respect to s, or do I use normal standard dz by ds? Do I use our normal standard d, or do I use partial? The answer to this is we should use normal d, because here you've got one variable coming in, and then it spits out one value. If you just look at this bit here, if you just look at this function here, you've got two variables coming in, the x and y location. So in this case, you have to use partial z with respect to x, because you've got two variables. In this scenario, you've only got one coming in, one coming out. That's why it's dz by ds as opposed to partial z with respect to s, because here you've only got one variable coming in, because we only used one variable to drive our particle. We only used one variable to drive our particle along here. So in this case it's actually dz, it's actually standard d as opposed to partial z, partial s. We don't want this because it's only one. If you look at our function, you've only got one variable coming in and it spits out one variable coming out. So you want dz by ds. So back to the chain rule. You've got to take the direction into account, the x direction into account, because now we've got to use partial, because if you look at this, just this bit only, you've got x coming in, y coming in, and then it spits out a z. So in this case, if you just look at this part of the function only, then you need partial because you've got two coming in. So now looking at partial derivative of z with respect to x, and then you times, in this case you use d, because if you look at the x location driven by s, remember we abandoned t, we are going to use s. So let me just change this. We abandon t and we are going to use s. So hang on. So now if you look at this, looking at this, do you use partial x with respect to s, or do you use standard dx and standard dx s. So looking at this, what you've got here is this thing here. You input an s and then you get an x location. So this is your function diagram. You input a variable s and then you get an x out. So in this case you've got one coming in, one coming out. It's not multivariable calculus scenario, it's a single variable calculus scenario. So in this case you would use standard dx by ds, not partial, because there's only one variable coming into the function. That's why you use d here. Well, anyway, dz by ds is given by this, and then you've got to take the y direction into account. So in the y direction, and then times dy by ds. So really you want to work out, well, the dy by ds is given by 4 over 5, and then dx by ds is given by negative 3 over 5. So that's this bit here and this bit here, and then partial derivative of z with respect to x. Well, this is our surface here, so differentiate it with respect to, partially differentiate it with respect to x. So that would be 8x. That would be 8x. Now partially differentiate it with respect to y. That would be 10y. That would then give you this. So we are now at this stage here, but then we want to evaluate it at that particular point where x equals 5 and y equals 2. So you would put 5 into the x, and then you would put 2 into the y. That would then give you this. So working it all out, it should come to negative 8. So the gradient in that particular direction at that particular point is negative 8. So when you come to communicate the partial derivative, because ultimately we want to find dz by ds. ds meaning the change. Well, this dz here is change in the height, the change in the height, the change in the height, the change in the height of our surface in the direction of our intended path, which is ds. So ultimately we want to find this. We want to find this. But when you come to communicate this, you need to specify the direction. We want to specify the direction by using the unit vector at a particular location. So some books would actually use df, because if you think about it, f is a function of x and y. Or you can imagine as z equals what. So you could use dz or you can use df. But you need to specify the direction, and you need to specify the particular point at which you want to evaluate the gradient. Okay, so our final answer is -8, but when it comes to the notation, you can use this or you can use this. Okay.